Okay, I think we can get started. So, good morning, everyone. Welcome to the GIS Sea Level Rise seminar. We're very glad to have Dr. Andrés Rivera, who is a geographer from the Universidad de Chile, with a PhD in glaciology from the University of Bristol in 2004. And at present, he is a full professor in the Department of Geography at the University of Chile, where he is teaching and researching. And he has conducted and participated in several projects related to glaciers located all along the Andes and Antarctica, using remote sensing, field data, and several surveying methods. Andres' research has been related to small glaciers in central Chile, glacier volcano interactions in central southern Chile, and calving glaciers in Patagonia. In Antarctica, he has focused his research in the West Antarctica interior plateau. And today he will be speaking on the topic main uncertainties in quantifying the contribution of Patagonian ice fields to sea level rise. So welcome, Andrés.
Yeah, well, thanks for the invitation. And I'm happy to be here giving this presentation that is a compilation of several studies that has been done in Patagonia, not only by me, of course. So maybe for some of you, this will be maybe a repetition of what you already know about Patagonia. I see that is Gabriela here, so she knows very well because she was working, for example, in San Rafael Glacier. But I think it's a good idea to have an overview of the main issues about the Patagonian glaciers and their contribution to sea level rise. Well, let's go to the talk. And first of all, I would like to say that Chile is the country in South America with more glaciers. We have about 26,000 glaciers in the final or in the last glacier inventory. Most of them are obviously in Patagonia, in Austral region, where the main ice fields are located: the northern Patagonian ice field, the southern Patagonian ice field, and Cordillera Darwin. In this talk, I will focus on northern and mainly southern Patagonian ice field, but the main ice bodies in Chile. As you can see here, we have a lot of small glaciers, glacierets, but rock glaciers also in northern Chile and central Chile, and very few outflow glaciers or the calving glaciers in a way, the main focus of this presentation. Northern Chile is in the main of the desert. We also have some small amount of ice, about 1% of the total. In central Chile, about 4%. Southern Chile, where mainly glaciers are located on top of active volcanoes, are about 6%. And then Patagonia, with the main chunk of ice, about 89%. In total, we estimate, well, not me, I mean, this is an estimation of the water cadastre, the main public institution in charge of glacier inventories. They estimated that in total we have about 2,572 cubic kilometers of water equivalent storage on glaciers in the country. As we will see later on in this talk, this number is totally out of discussion because it's based upon just an estimation, a very rough estimation based upon the area, but no based upon real data. And we will see that only in the southern ice field we have more ice than this global estimation. Anyway, in one of the most recent papers about Patagonian glaciers, the main estimation of the total ice equivalent in the region is in the order of 5,350 cubic kilometers of ice. This is more than all the glaciers in the Alps, and it's about 6% of the glaciers worldwide, excluding, of course, Greenland and Antarctica. And based upon this paper that is a joint compilation led by Johannes Furst, the Patagonian glacier have the potential to rise sea level by about 15 millimeters. The main problem that we have in Patagonia are what is going on with these glaciers? Why are they changing? Are they responding to climate change, or the glaciers are decoupled from the climatic signals, and there's some other factors explaining what is happening with them. We will see some of the recent changes we have observed, and we will see if this is something that we can consider as potentially real, or maybe there are some big uncertainties related to the future contribution of the glaciers in Patagonia. A bit of background about the climate signals in the region. This talk is not about climate change or about the main climatic driving factors, but this is the first figure with the annual temperature, air temperature in Patagonia, in southern Chile, based upon reanalysis, ERA 5 reanalysis data. And you can see here that in general, the southern region is experiencing a clear warming signal, with different rates depending on where you are. But interestingly, the northern Patagonian icefield is more, there is a more clear signal, but looks like, or seems to be, that the southern icefield is maybe not very clear. It doesn't have a clear air warming trend. And then Cordillera Darwin. We did the comparison between this reanalysis data that you already know, that is a coarse resolution, based upon models and not necessarily validated, etc., etc. But we did a comparison of this data, for example, with Cochrane. It's a one station that is continuously operating in the region since the 60s, 1961. And here you can see that there is a quite good correlation between both series. The blue one is Cochrane, this automatic weather station that is collecting data continuously near an airport in the region on the western side of the northern Patagonian icefield, and compared to reanalysis data. So the first message here is that there is a high variability in annual values around some anomalies, of course, but with a clear warming trend in the order of 0.21 Celsius degrees per decade in 1K, based upon the station, and about 0.16 Celsius degrees based upon reanalysis. It's a not very strong trend in the southern icefield, but it's more clear in the northern icefield. Based upon this similar data, Minowa, in a paper that was published in 2021, was using the skin temperature in Patagonia, and he was also detecting some warming trends in the northern Patagonian icefield, about 0.25 Celsius degrees per decade. But also he got an important value, similar value, even stronger in the southern icefield, that it was not very clear in the data I showed you before. But they did a good comparison, as I have done, between ERA 5 reanalysis and Perito Moreno. It's an automatic weather station in the region. And it looks like there is quite a good correlation, between both data sets, ERA 5 and Perito Moreno. So there is some confidence that the reanalysis data is expressing what is going on, at least in the northern icefield, where I did the comparison here in Cochrane. I presume you are seeing my mouse. Do you see my mouse? Yeah, okay. So here is Cochrane, the station I was showing before, and Perito Moreno is here, also on the eastern side of the Patagonian icefield. Yeah. Regarding temperature, this is regarding temperature. I mean, regarding precipitation, Well, we are talking about a region with some of the highest precipitation rates in the whole world. It was considered one of the wettest in worldwide, but more recent estimations are indicating that maybe it's not as a world record, but are having some regions, some specific basins and areas where the precipitation is extremely high. So here you have again ERA 5 reanalysis data of annual average solid precipitation between 81 and 2010 in northern icefield and in the southern icefield. And you can see the amounts are in the order of 6 meters water equivalent as an average in this during this 30 years period. But the main factor here are the differences between the western side and the eastern side of the in Patagonia, because the Andes are having a very strong blockade, mountain blockade, that is obviously generating a shadow of precipitation to the east and very strong precipitations on the western side. Here you can see in this upper figure here the some of the stations that are measuring precipitation in the long term, and you can see on the western side here you have the longitude. So on the western side the precipitations are above 2,000 millimeters per year, and then on the eastern side, the Argentinian side, let's say, and also the Chilean eastern Andes, the precipitations are smaller than 500 millimeters per year. So it's a very clear shadow effect. It's a desert on the eastern side and very wet on the western side. And what's going on in the middle? Well, in the middle are the southern Patagonian icefield, the northern icefield, and this is just a profile on the western side, on the eastern side, sorry. So you have very small precipitation at bottom, and then on top, these are real measurements of precipitation are quite strong in the order of 8 to 10 meters annually. Yeah. So we are talking about the region with a strong spatial variability of precipitations, east, west, and also north, south. And here you have a more recent estimation of Sauter that was published in 2020 with different models, and because there are not many stations. Here are some of the stations in the whole region, but here he was using, models for estimating the precipitation in the region. And here you can see the numbers. These are the numbers for the more realistic model that for the southern Patagonian ice fields are indicating about 5 meters water equivalent per year. And for the northern icefield, a bit higher in the order of 5.4 meters water equivalent for this period, 2010 and 2016. But then, and here you can see that the highest peaks of the icefields are having more than 8 meters water equivalent, and the lower parts about 4 meters, water equivalent. What about the trends? Well, these are estimations based upon ERA 5 or ERA 5 reanalysis. I'm always saying ERA 5 because my Spanish, Anyway, ERA 5 reanalysis, and you can see that the Vietnam Basin that is located here in this box, quite in the middle of the southern Patagonian ice field, we have some very strong variability since 1980, but with a trend of positive precipitation in the order of 104 millimeters water equivalent per decade. Yeah, the northern ice field is showing this number 92. The northern part of the ice field about 103, the southern part about 97. So let's say that Vietnam is like in the middle of a bit higher with a positive trend. So the general background is that we have some small warming and a more clear positive precipitation trend. In colors in the background, you can see the trends, the clear drier conditions in central southern Chile, and then the positive trends in Patagonia. Yeah, here is Puerto Montt, about 40 degrees south in latitude. Central Chile, for example, is experiencing a very drier trend with a mega draw observed in the last 12 years. So the contrasting behavior of the contrasting trends in Chile are very amazing. Very drier conditions in central Chile, central south, until 40, and then a positive trend further south. So what we can expect in terms of Patagonia regarding the mass balance, in comparison with the snow accumulation. Well, these are some estimations by Sauter that is comparing the southern compared to the snow accumulation, and there is a clear correlation between both. So if you have obviously higher snow accumulation, you have higher surface mass balance. There is a good agreement between both, and indicating that more likely is the precipitation that is controlling the mass balance, the surface mass balance, more than the temperature. And here you have in these colors some estimations of the surface mass balance for different studies. And in general, for example, I prefer to mention Schaffer, that is having high uncertainties, but the positive values for the southern icefield, and in here for the northern icefield here on the right, also a bit negative, but with high uncertainties. Yeah. Brown is showing some negative values for the northern icefield and very negative value for the southern icefield. But in general, the main estimations that is used by different works and models is based upon Marius Schaffer, that is showing some positive mass balance trends in the southern icefield and a bit slightly negative trend in the northern icefield, but with high uncertainties. Well, the result of the combination of these factors, I mean, in terms of what is normally thought the main driving factor, the climate, the main conclusion of that is, or the main expression of that in terms of the glaciers, is this very strong negative mass balance that was estimated by Michael Semp or 6 years ago in Nature, that is showing that almost all glaciers all around the world are showing negative cumulative specific mass changes in meters of water equivalent. But obviously Patagonia here, or the southern Andes in this color here, like brown, are the highest, having the highest rate. And if you consider here the cumulative mass change in terms of sea level, Patagonia again is the second highest, only after Alaska. And the estimation is that Patagonian ice losses are equivalent to 4 millimeters of global sea level rise since 1945. So, I mean, if the climate in the last 2-3 decades are showing some slight warming and even a positive precipitation trends, why these extreme negative mass changes in southern Andes? Well, we know that the glaciers are thinning, are retreating at very high rates, but there is also a positive surface mass balances, not everywhere, but in most of the glaciers. There is a strong total mass change. That means that there is a partially decoupled mass budget compared to the climatic signals. Therefore, the mass changes are primarily caused by probably a dynamic adjustment of the calving glaciers that are the main glaciers in Patagonia. Because these calving glaciers, freshwater and tidewater glaciers, are experiencing the more significant thinning rates and the highest calving fluxes. So this decoupled signal is more like what several authors are proposing is due to this dynamic adjustment with some delays, but ultimately triggered by the climate, of course. Something is happening with the climate that is affecting the glaciers, and they are thinning very rapidly, calving at highest rates, and explaining most of the mass changes. But the problem here is that the uncertainties, because we know up to now that the climate variability is quite high. The surface mass balance is mainly estimated by models and not by direct measurements. Ice dynamics is better known because already we have different methods for estimating the ice flows, for example, using feature tracking techniques. But the frontal ablation, the calving, is less known. The calving, I don't need to go into much more detail, but it's the amount of icebergs that are produced by the glaciers calving into lakes or fjords, plus the subaqueous melting, the melting is taking place below the water, plus the surface ablation at the front, and the frontal changes. So here are the main problems that I think are the most significant contributions to the uncertainties, especially because these kind of glaciers that are calving into these lakes are controlled by the bathymetry, are controlled by local factors that are explaining how much ice is lost at the front. Actually, the water depth and the connection between the water depth and the near floodability of the glaciers that in this case, where most of the glaciers are temperate, are generating a negative effect because they are disintegrating when the glaciers are reaching these floating conditions. Compared to Antarctica, there are some big differences. In Antarctica, we have glaciers that are flowing into the ocean, but the ice shelves, you know, and they are still connected to the glaciers, and they are at the front of the ice shelves. You have calving, of course. You have huge tabular icebergs that are breaking out, but there are 700 kilometers long, ice shelves connected to the main glaciers coming from the interior, connected at the grounding line. But here we don't have floating tongues, apart from maybe one or two examples. So the grounding line in Patagonia is at the glacier front, because as soon as the glaciers are reaching floatability, they are disintegrating and calving away. So this is controlling, as in Antarctica, by the way, in Antarctica, the grounding line is one of the most important factors. What is happening with the grounding? Is migrating or not? Is having an increase melting because the ocean water that is coming in underneath the ice shelf is explaining the melting and therefore the migration of the grounding line, etc., etc. Here also is the same. But in Patagonia, the grounding line is at the front in most cases, apart from maybe one or two examples. So these are the uncertainties I will be talking about today. Okay, so let's go first to the northern Patagonian ice field. It's about near 4,000 square kilometers of ice, about 48 basins, higher than 0.5 square kilometers. Only one tidewater calving glacier is San Rafael. By the way, this is reaching the Ecuador worldwide, with some maximum thickness about 1,500 meters and maximum velocities of around 20 meters per day. In yellow here, San Rafael, the only tidewater glacier, but several other glaciers are calving into freshwater lakes. So the same kind of process, but into lakes or just one into the ocean. San Quintin here is one of the glaciers I will be talking about. Was grounded until recently, but now there is a new lake that was formed at the glacier front. So this is one of the papers that was by Haber, 2018, that was estimating the mass balance based upon the geodetic method, comparing different digital models. In this is RTM from year 2000 and Tandem X from, well, two dates, 2010 and 2012 and 2016. And here you can see in the scale on the left, you can see that most of the northern icefield is having, a negative elevation change in terms of meters per year. And the main calving glacier here, tidewater calving glacier, is having some negative values in the long term and the shortest term, but it's not experiences the highest thinning rate. The highest thinning rates are here on the western side of the ice field. But even the upper parts, the accumulation areas are experiencing some negative elevation changes. In terms of the mass balance in gigatons per year, Foresta was showing these estimations comparing different models, and almost all of them are showing negative mass balance in the order of between 5 and 6 gigatons per year in some of the recent periods. In the more longer term, also some negative values, but maybe a bit smaller. Yeah. In yellow here, the glaciers without very good data. So which glaciers are explaining some of these changes? Well, one of them is Rafael. Here is nice because we have a longer historical record of this glacier. This is the first lithograph or painting of the glacier in 1871. This is in 1944, the Trimmetrogona aerial photograph, and 2003, and the total compilation of the glacier front. So in this case, we have at about near 11 kilometers frontal retreat. But the bathymetry is important, but not very important, because the maximum water depth I was measuring here was in the order of 250 or something like that meters. Unfortunately, I haven't been here, or as far as I know, nobody has been very close to the glacier front at present, so we don't know the bathymetry here. So this is one of the big issues. Maybe Gabriela knows better the bathymetry near the present glacier front. But from here approximately to the west, the bathymetry is not very deep. And maybe that is explaining that the frontal position of the glacier is quite stable, and even with some negative elevation changes as described before. This is another example, Glacier San Quintin. This is 1944, Trimetrogon, 2003, and 2022. This is an interesting case because it's a Piedmont glacier that was grounded here at the frontal moraine, coming basically from the Little Ice Age. And now you have a very big lake, not only at the front, but also at the margins of the glacier. So in between 93, that was the last time the glacier was against these moraines, until now, the glacier is now calving into freshwater lakes with a total area of about 45 square kilometers. In this case, this is one interesting example because we have no idea about the bathymetry of this lagoon. Yeah, there are no measurements of the bathymetry. We have estimations of the surface topography coming from SRTM and Tandem. We know the velocities from feature tracking, but no idea about the water depth, and very few data about the ice thickness. Especially because near the front, the presence of water, yeah, especially underneath the ice, between the ice, everywhere, is precluding the radar signals to penetrate the ice and showing a very clear bottom reflections, allowing us to estimate the thickness. But using the available data and the most recent radar data, we know that the glacier at present is probably floating. The lower part of there is a small portion of the glacier that is already floating, and it's not breaking away from the main glacier coming from the interior. And this area that is floating is disintegrating very rapidly. Yeah, that's why the retreat in recent years is quite strong. But there is an area here that is close to flotation, yeah, and it's probably going to melt away or calving away in the future. So what is happening at the moment is this glacier is having a strong thinning, yeah, but we don't know if this thinning will trigger a dynamic adjustment with increasing velocities, for example, dynamic thinning with a strong retreat of the frontal position of the glacier, because our the data we have of the subglacial topography is not the best upstream near the lake. We have better estimations of the ice thickness at the top of the ice field because there are several profiles, but there are only one or two profiles going down the main trunk and with some problems due to the presence of water. So in this case, for example, this is the only case where we have at present, we know that the glacier is floating, at least a part of the glacier. I know that other glaciers in the southern icefield, for example, were close to flotation and maybe were floating, especially, for example, in Gray Glacier. Why we know? Because in some occasions, a calving event produced or generated a huge tabular iceberg that is normally associated to floating conditions. But this is not something very common in Patagonia. So the main uncertainty here, again, is are the glaciers floating or not? How thick is the ice upstream the present position of the glaciers, and how deep is the water at the glacier front? Because these factors are the main triggers of the dynamic adjustment more than the climate signal. And this uncertainty could be expressed here in these models of the northern Patagonian icefield, where you have different models of ice thickness, and you can see the strong differences. So, for example, A is the last compilation by Furst. I was involved on that. But then you have different estimations, like the one by Carribig, Millian, or another one from Millian, etc. And you can see that depending on what kind of models you are using, you are having different compilations of the subglacial topography. And this is quite important because if, for example, there is a subglacial connection between the ocean and the interior of the ice field, where the accumulation area is located, maybe the changes in the future will be much more strong and much more bigger than other areas that already are grounded and and they don't have an inverse subglacial topography upstream. So this is the main uncertainty here, in spite of the recent advances by this compilation by Furst that was using all available, including all the data we have collected in recent decades. So let's go to the southern Patagonian icefield now. So we are talking about 350 kilometers long, 60 to 90 kilometers wide, east-west in the northern part, but maybe only a couple of kilometers in some areas like the Fayerracher here or around Fiordo Calvo here. But in general, it's a continuous ice mass in southern Chile and Argentina. Most of this is in Chile, but some of the glaciers on the eastern side are located in Argentina. In blue here, you have the basins, the main basins of the ice field. Also about 48 main glaciers. I'm not talking about the smaller glaciers. And the area is about 12,000 square kilometers. The northern one is about 4,000, so we're talking about 2.5 times bigger than the northern icefield. It's temperate as the northern icefield, with also maximum ice thicknesses near 1,500 meters and maximum velocities in the order of up to 30 meters per day, a bit higher than the velocities in the northern icefield. But the most interesting thing here are the behaved glaciers. Here on the upper part, you have the Corgemont in the northern part of the icefield that is retreating very strongly during the last 120 years. Then you have P11 here in this area here. That is the only one, or maybe one of the very few glaciers all around the world that is advancing since the mid 19th century, when the first maps of the glaciers were drawn by the British hydrographic expedition, the same of Darwin, but not with Darwin, with another guy called Parker King, but the same expedition. They went to the area, and this was a fjord, and they found a beautiful fjord with some icebergs at the end, and now all the area that they were navigating is occupied by ice. And then you have other glaciers with different rates of changes, but in general, with strong retreats and thinning, apart from pions. Well, Corkimon, as I told you, is totally out of balance. It's still retreating, very high velocities, high calving fluxes. O'Higgins was retreating very fast until the 80s, and then was quite until the 90s, then was quite stable, but in the last 10 years is retreating very strongly again. Beyonce still advancing and thickening after almost 80 years continuously, because in between the mid 19th century and the mid 20th century was some oscillations. The glacier advanced and then retreated. But from the mid 20th century, 1945, the glacier is almost continuously advancing. Now it's still destroying trees very close to the forest. It's the only example in the southern ice field. In Cordillera Darwin, also, there are a couple of glaciers that are very close and destroying trees, but the only one in Patagonia is Pionce, and then, well, also on a small glacier here that is connected to Pionce, that's called Trinidad. And then further south, well, Gray, Tyndall are also retreating, Dixon also in Torres del Paine here in the southern part, and in Argentinian side, Vietnam, after a long-term stability, is retreating very fast in the last 10 years. Uppsala was retreating very fast, but then has been stable in the last 10, 20 years. And Moreno, that was also advancing, was one of the famous glaciers in the world that was advancing, or was very close to the Magallanes Peninsula, touching the rock, damming the Brazo Rico, one part of the Argentino lake, and then going back. And well, it's a very nice place. But now, in recent years, it's retreating. And there are several indications that maybe will be a catastrophic retreat, because again, the bathymetry of the lake upstream, or the bathymetry of the lake and the thickness of the ice is quite deep, maybe upstream in the first part close to the Magallanes Peninsula is an inverse topography, so the glacier probably will retreat quite fast. Yeah. So let's compare the elevation changes in the southern ice field, and here you have a more contrasting behavior. You have glaciers with very red colors here, indicating the thinning rates, especially Jorgemon in the north, and all the western side up to Pionce here, and then on the eastern side also with very strong thinning rates. But if you see the red color, with the maximum thinning, are located at the bottom, or the ablation areas. The accumulation area is thin, smaller rates, but the lower part of the glaciers are thinning very rapidly, at very high rates, and this is a clear response to the calving fluxes at the front. Pionce is the only example with positive values, with thickening. You can see here the scale. And then south of Pionce is quite stable, very close to balance, with some negative numbers again in Torres del Paine, in the southern part. Then in the most recent period, in this study by Haber, you have that the same rates, but with more negative thinning and more positive thickening. Yeah, so there is more contrasting behavior. Still, the northeast, northwest, and east are thinning very rapidly. Then Pionce is stable, and then all the southern part is thickening, especially slightly, especially at the accumulation areas. But the glaciers in Torres del Paine here is Dixon, Olvidado, Frias, and Gray and Tyndall with some thinning. The total compilation by 40 some very strong mass balance. Here again in gigatons per year. Maybe this paper that we wrote together with Eric Grignot and Gino Casassa in 2003 is a bit of the trend, because we were using short period of time between 95 and 2000, but all the other estimations are in the long term are indicating, some negative values with between 10 and, let's say, 20 gigatons per year. The area changes, apart from this strong thinning, we have a strong area losses in Patagonia. Here you have an estimation in 1945, and then in 2021, with some acceleration in the area change rates between 20 up to 33 square kilometers per year. This is the number, square kilometers per year. This is the area lost per year in the most recent period. But in the long-term average is about 24, 23.5 square kilometers per year area losses in Patagonia. But with this strong contrasting behavior, here you have 100% in 45, positive changes, area changes, NPOC, and all the rest negative values. So what is explaining these changes, in my point of view, is mainly connected to the tidewater calving cycles, that the glaciers that are calving are connected to the bathymetry with the local factors at the glacier fronts, where you have different phases of this tidewater calving cycle that was proposed by Post many years ago. But it's confirmed here with some advancing glaciers or stable glaciers that are building up a frontal moraine. But then when climate are having negative effects on the glacier, on glaciers, they are retreating, and especially when the bathymetry is quite deep, like in most of the cases in Patagonia, the retreat is extremely fast. This has been observed in Uppsala, in O'Higgins, etc., until they can reach again some stability, where the ice is grounded, there is almost no floatability and more stable conditions. When the glaciers are along this phase, these areas with very deep bathymetries, the glaciers are reaching floating and are breaking away easily. And then the subaqueous melting also is important, but depends on the circulation of the waters, of the water in the lakes, especially if the water is quite stratified or not, or if there is a mix at the front, or if there is an intrusion of warming water from the ocean or from lakes. But we will see that this factor is not very strong, it's not very important in terms of the total magnitude, but the main factor is the calving, the frontal ablation due to calving, especially in deep lakes. So this is one example. Let's go into more detail. This is Jorge Montt Glacier. This is a map from the end of the 19th century, and another one from the same area. And here you can see Jorge Montt. Yeah, it's not very clear probably from your perspective. That's why I'm zooming out, zooming in. Yeah, and so this is the glacier at the end of the 19th century. Now, all this area here is a fjord, and the glacier is 24 kilometers south from this position. So the isla that I was showing before is outside the screen here, having the same scale is quite complex. But now from this island that is, let's say, is retreating into this. I have been following this in recent years, and it's still retreating without any pause. And in total, the total frontal retreat is in the order of 24 kilometers. So here you have a compilation between, so this is the position at the end of the 19th century, this is 76, and then in recent years is about here. So all this new fjord is replacing the ice that was observed at the end of the 19th century. Yeah. Well, interestingly, in this case, yeah, we have the surface topography in different dates. Here you have the surface topography, subglacial topography, estimated bathymetry measured by us in this paper, and in this along this longitudinal profile from 1986 to 24 in this area here, and then up to the divide, the upper part of the ice field. And you can see here that the strong retreat between 86 and 2000 was in connection with this deep fjord with the order of 450 or something meters. Unfortunately, this estimation with the bathymetry, with gravimetry, is not very accurate. I'm not showing here the uncertainties, but we really don't know if this is real or there some strong changes, but up to now, looking into the retreat that this has been observed of the glacier, probably this area is much deeper than estimated before. So this estimation upstream is quite uncertain, and hopefully there is a threshold here about 5 kilometers from the present position of the glacier where the glacier will get some stability and will be grounded and not close to flotation and will stabilize. In this case, the calving will reduce and probably the propagation of the thinning upstream will diminish, will be much smaller. What is the dynamic that was observed by us in Jorge Montt? You know, here you have velocities. Here you have the colors for each year. This is based upon the ITS Live NASA dataset. And you can see here that between 86 and 2001, when the glacier was retreating much faster, there was a huge increase in velocities. Here you have the velocities in meters per year, per annum. Per annum, and you can see that the glacier moved from about 1,200 meters to even 4,000 meters. Then the velocity was reduced a bit, and increasing up to now, up to 2022, the last time I did the analysis, where the front of the glacier here was moving at about 5 kilometers per year. Yeah, so this is how the frontal changes I was showing before is affecting the dynamic upstream the glacier. The front of the glacier is around here, you know. This is the front of the glacier in 2022. This was in 1986, and these are the profile upstream as shown here. Yeah, so hopefully the glacier, when the front is keep going with the retreat, this region will grounded. In total mass balance components, you can see here in colors the accumulation, surface melt, frontal ablation, total surface mass balance, and total mass balance. In the total mass balances are very clearly very negative all during this period, yeah, with the main factor being accounted by the frontal ablation, namely calving plus subaqueous melting. In the accumulation in the area is not very strong, but anyway, is in the order of 1 meter water equivalent per cubic kilometers of water equivalent per year. But the frontal ablation is the dominant factor. That's why that is explaining these negative mass balances. But we don't know in the future if this will maintain the same rates because we don't know certainly the subglacial topography. Another example here is Glacier O'Higgins. It is also experiencing some negative trends. This is in 1945. It's a very interesting example because in 1945, you know, this Glacier O'Higgins was extending into the lake and was deflecting this other glacier, Glacier Pirámide, into this valley called Escondido. But look at this, in 1975, the glacier was retreating, and the main direction of this glacier was shifting, was turning, to the north. North is upstream here. And then in 2000, when the glaciers kept retreating and the lake was expanding, this small glacier was flowing to the north. So after losing the support of the main glacier, all other small glaciers around were changing ice flow and directions, and also accelerating in some cases and thinning in other cases. This is the situation in 2024. So this is a new lake, totally new lake, that was open in recent years. You can see here in year 2000, the glacier was around here and kept this position until 2016 approximately, and then began to retreat again between in the last 5 or 7 years, with a new lake. So this is the compilation of the retreats. Here you have the years and the position, even outside the screen, just to show you how it's retreating. But this is 2024. Yeah, the area increase in these rates in recent years. So what is driving these changes? Well, we did the bathymetry, the first bathymetry near the glacier in recent years, because previously was an estimate we conducted also in year 2006 a bathymetry of the lake out a bit far away from the glacier front. Yeah, but in more recent years we did the survey of the area close to the glacier using a sounder and an echo sounder, and also a seismic system called bubble pulsar. And with that, we compiled the bathymetry of the area. And amazingly, the maximum thickness was coincident with the area where the retreat rate was much higher, and around, with 820 something meters water depth. That was the water depth of the lake around this red color here, as we measured years ago. At the present, at the front, at the present position of the glacier, the water depth is not as deep as here, but again, we have about 600 meters water depth. This is one of the deepest lakes on Earth. Here is one of the records of the bathymetry with this seismic system, and you can see, well, here is the profile, H prime is here, H primes or whatever, yeah. And here you have the rains at the bottom, with very complex topography at the bottom, but the deepest part here outside the present position of the glacier is here on the left, and this was the deepest part of the lake, about 800 meters, far away from the present position. The glacier was stable around here for many years, but now it's retreating again. Unfortunately, I haven't been there in Rivera, so we don't know exactly what is happening with the glacier at the present, at this position of the glacier. This is the water temperatures and our estimations of the melting, the underwater melting, and it's not quite high. But anyway, we're talking about 30 meters per year of melting at the bottom of the temperatures here also show. The velocity is also, the glacier is increasing velocity in connection with the retreat, with some delay in the 1 or 2 years. Again, the profile, the longitudinal profile from the upper part of the glacier, the accumulation area, the ice divide, until the bathymetry, the front at the end of the 19th century. You can see surface topographies, estimations of the subglacial topography, high uncertainty in all of the models. Here you have the models, Milan, Farinotti, Carrivic, with very strong change. But with the bathymetry in black, the one we measure here, that is quite contrast or quite different from the subglacial. And here are taking place the changes, especially the huge calving and the frontal retreat. So we need to improve our estimations of the subglacial topography upstream. This is in red. Well, the red color is the first 2024 estimation of the subglacial topography. That is more or less in the middle of all these estimations, but again, we have a strong discrepancy here. So again, we know for sure that it's not right, the subglacial topography, of course. I mean, I'm co-author of this paper, so I'm talking about myself in this way. We know that these subglacial topographies are having high uncertainties, high errors. But anyways, it's the best compilation up to now. But we know that in the area where the glaciers the changes are taking place, there is a strong discrepancy. And these are the calving, the mass balance fluxes. It's very negative with some positive surface mass balance, but in globally negative due to the calving, in this case in O'Higgins Glacier. And the calving fluxes in recent years, all negatives, mainly explaining the total mass changes. The last example I will show you is Vietnam. I know that I'm running out of time, so I will skip several things here, but there are many interesting stories about Vietnam glacier, but I will move forward because the time. But this is one of the main glaciers in Patagonia, and this is the picture that was taken in 1916, and this is more or less how it looks like the glacier at present. It's a new lake without ice, or the ice is very far away from this position. This is a complete frontal changes of Vietnam Glacier that was very stable until the year 2000, and then in recent years is increasing the retreat very strongly, and at present the retreat is in the order of 500 meters per year. Yeah, is amazingly is retreating very fast. The first time I went to the area, I was 2014, and the glacier was around here. And now it's all this area is new. So we did the survey of this area because the photograph we installed in this area were like this in 2014, and now it's like that. So we're taking photograph of a lake. That was not the idea. But we know that the area is having a strong calving because there are some beautiful videos in YouTube with subaquatic calving events, like ice foods coming out the lake even 300 or 400 meters away from the present position of the glacier. So we know that this is probably a very deep lake. So we did the velocities again. I have no time for that, but we did the bathymetry, and we found that the area is quite deep. Yeah, these are some estimations of the temperature of the water, quite stratified in this case, so meaning very small mixing and not very strong melting. But here maybe you don't see down there, but when we approach this area that was recently abandoned by the glacier, we found that we were talking about, and in total, the maximum water depth we found was about 900 meters. This is the deepest lake in the whole Americas, including the US, Canada, and the whole Americas, and number 5 or worldwide. This is very extremely deep lake. In these conditions, at present, the glacier is the front of the glacier is the grounding, and as soon as it's very close to flotation, is breaking away, and that is explaining the high fluxes observed in the area. This is like a video of the bathymetry near the glacier front. The present glacier front is a very extreme, very deep fjord where near 990 meters ice wall, 90 meters around, 90 meters above lake level, and 920 meters below lake level. But again, we don't know for sure how are the bathymetry, the subglacial topography are upstream, but we know that the glacier is quite deep. This is an estimation by an Argentinian colleague. the glacier is quite deep, more than 1,000 meters. So more likely, if these conditions are confirmed, the glacier will keep retreating very fast in the future. These are the estimations of the main components of the mass balance. Well, and here is the estimations of the topography and the subglacial topography. So again, here you have the discrepancy in colors, the discrepancies between the subglacial topographies in the area, quite strong. But the last model we have compiled together with Lanuti is probably more accurate because we're using bathymetry, the recent bathymetry, as a fixed point at the bottom and some ice thickness. But again, the future of the glacier, the future level rise of the glacier is not certain because we don't know how much bathymetry. Anyway, I have no time for much more, but here is the last numbers, and this is the comparison between the different models in terms of the total volume in Patagonia. And you can see that the uncertainties, the last study by Furst is showing for the northern icefield this number about 1,156 square kilometer cubic kilometer ice, plus minus almost 400. Amazing. Only the numbers around the southern icefield are double of the estimation by the Chilean water cadastre. So this is showing you the uncertainties are retreating, etc. And the trigger must be the climate warming very strongly, but it's warming. But the water depth, especially the water depth, is controlling the frontal changes and the velocities at the glaciers that are the most of them are calving in the southern icefield, especially also in the northern icefield, but especially in the southern one, and meaning that the glaciers in the country are losing mass at very high rates. In terms of the Patagonia, we think that the buoyancy conditions at the glacier fronts are driving the main changes in a similar way of the peninsula, the Antarctic Peninsula, in terms of the grounding, but in understanding that the grounding is at the front of the glaciers. The subglacial topography upstream is not very well known in spite of the recent advances, but unfortunately, most of the cases we have seen are inverse. So it's getting deeper upstream. So in the present conditions, the glacier will increase the calving rates because they are getting close to floatability easily into the future. So these are some of the ideas, some of the data I wanted to show you. I hope this was interesting for you, even if you knew about what's going on in Patagonia. Thank you.
Thanks very much, Andrés. It's quite interesting. Do we have any questions? A little bit over. Yes, Jeff. Jeff had a question. Jeff, you are muted still. Okay.
Hi, is the has anyone done an ice core of the accumulation area to look at what the history of accumulation is and how old, what the turnover time of the glaciers are?
Yeah, there are at least 3 ice cores that were collected in Patagonia. 2 of them, I was involved in 2 of them, in all of them, in the 3 of them, but they are quite shallow. For example, the one we collected at the upper part of Pion's Glacier, 2006, 2013, was about 46 meters long. The same in Tyndall, only about 40 meters long. And due to the temperate condition of the ice, close to melting, we only, well, the guys who were expert on that, mainly Margit Tchaikovsky, probably you know her, from Paul Cherier Institute, we were able to estimate mass balance on only a few years with very high rate. That estimation was in the case of P11 core, that the annual accumulation was in the order of 7 meters water equivalent per year, but only for about 10 years. So there are no ice cores going to the bottom of the ice field. Because mainly the general knowledge about this is that we're not getting a clear climatic signal due to the, but maybe using different methods, we can drill down to the bottom and anyway try to get the age of the ice, which is up to now unknown.
Thanks.
Okay, great. Any more questions?
Mike, I think Mike Kaplan is having one question.
Sorry, I came on late. Had another meeting.
Oh.
I do have a question. Nice talk and nice to see you, Andres. So many of the calving glaciers at some point will start to become grounded again, right? They'll retreat out of the lakes and the fronts, like the outlet glaciers in Greenland. Eventually, the calving will slow down, right? But that will probably vary from glacier to glacier, and I assume could take decades or a long time, or you know what I mean? Many of the glaciers, like Kayukeo, for example, is no longer in the lake because it's retreated so much. But then other things like Uppsala, I guess, will be in the lake contact for a long time. But I assume this will take decades before many of the glaciers will no longer be in contact with the lakes because they've retreated so much. And something about, my question is something about, will this happen over the next few decades, or it really varies from glacier to glacier?
Yeah, I think it will vary between basins. In some cases, I think in only a few more years, the glacier will get out of the lakes, let's say no calving anymore. Especially where the slope near the present fronts are quite steep, indicating that the subglacial topography is quite, or the thickness is quite shallow. I think only in some cases, like Dixon, for example, Dixon Glacier was retreating very fast in recent decades, and since 2018 or so is quite stable because new rock outcrops are appearing. Gray also are showing new rock outcrops at the front. But for example, in O'Higgins, it's still retreating. We don't see any rock outcrop at the front, no island, nothing like that. But the surface slope is rising, so probably will take a few more years or maybe decades until it's getting totally grounded. Vietnam, I'm afraid, is take decades of long retreat. And Jorge Mon also, because we are talking about several kilometers before the subglacial topography is probably above the present lake levels. So yeah, will depend on the glacier.
So yeah, for many years, decades, the glaciers will still be accelerated calving.
Yeah, my feeling is that in most of the cases will be like that. Yeah, yeah. But, you know,
Thanks.
Okay, any more questions? I guess we can stop there. So thanks again, Andres.